In 1939, the last naturally occurring element on Earth, francium, was discovered. However, the periodic table of the elements still wasn't full. The next year, a non-natural element was discovered, plutonium. This new element had fascinating properties which made it incredibly useful and incredibly dangerous. Learn more about plutonium, how it's made, and what it can do on this episode of Everything Everywhere Daily. This episode is sponsored by Brilliant.org. Brilliant's mission is to inspire and develop people to achieve their goals in science, technology, engineering, and mathematics. One person, one question, and one small commitment to learning at a time. They enable great teachers to illuminate the soul of math, science, and engineering through bite-sized, interactive learning experiences. Their courses explore the laws that shape our world, elevating math and science from something to be feared to a delightful experience of guided discovery. If you're interested in learning more about any STEM subject, go to everything-everywhere.com/brilliant. Once again, that's everything-everywhere.com/brilliant. To start a discussion of plutonium, we might as well start with what it is and where it comes from. Plutonium has the atomic number 94, which means it has 94 protons. Its discovery is credited to Nobel laureate Glenn Seaborg, who discovered 10 different elements on the periodic table. If you remember back to my episode on the element uranium, which is element 92, it was given its name from the then newly discovered planet Uranus. Just months before the discovery of plutonium in 1940, element 93 was discovered by bombarding uranium with a cyclotron, and it was called Neptunium, the next planet after Uranus. Then, later that year, Seaborg and his group at the University of California, Berkeley bombarded uranium with deuterium, a hydrogen isotope, which created element 94. And it was named after the planet after Neptune, or at least it was at that time, Pluto. Only a few atoms of it were actually ever initially created. The abbreviation for plutonium is Pu, even though it really should be Pl, and there are no other elements with Pl as an abbreviation. Seaborg thought it would be funny to call it Pu, and the abbreviation stuck. As I mentioned in the introduction, plutonium isn't considered to be a naturally occurring element. However, that isn't 100% true. There are actually extremely small amounts of naturally occurring plutonium on Earth. A study published in May of 2021 found an extremely small trace amount of plutonium on the ocean floor, which was believed to be residual from the formation of the solar system. Likewise, there's also very small amounts that are created through the natural radioactive decay of uranium. In 1942, after the first controlled nuclear fission reaction took place by Enrico Fermi at the University of Chicago, enough plutonium was finally produced where its physical properties could actually be studied. The process of nuclear fission is how almost all plutonium is created. There are 20 known isotopes of plutonium, but only 2 that are widely created: plutonium-238 and plutonium-239. Plutonium-239 is created when a uranium-235 atom splits, ejecting a neutron which is captured by a uranium-238 atom, turning it into uranium-239. A neutron then engages in beta decay, turning into a proton and ejecting an electron, turning it into Neptunium-239, and then a second beta decay occurs, turning it into plutonium-239. Plutonium-238 is created by uranium-238 capturing a deuterium atom to become Neptunium-238, and then a beta decay occurs to become plutonium-238. And no, there will not be a quiz at the end of the episode. If you remember back to my episode on uranium, the 2 common isotopes of uranium were 235 and 238, and they behave differently in nuclear reactions. In particular, U-235, which only constitutes 0.7% of all natural uranium, is the stuff you need to make bombs and nuclear reactors. It's called fissile. By the same token, plutonium-238 and plutonium-239 behave differently in nuclear reactions as well. Plutonium-239 is fissile just like uranium-235. That means it can be used in bombs and reactors. In fact, the atomic bomb that was dropped on Nagasaki, nicknamed Fat Man, was a plutonium bomb. Plutonium-238 is not fissile. However, it's highly radioactive with a half-life of only 87.4 years. And I'll be talking about that more in a bit. So, what are the properties of plutonium? What's it like? Plutonium is a metal. Physically, it has a silvery appearance like most metals. However, it oxidizes quickly, which can change its color. It has the unique property of not being magnetic. It will also expand and shrink from heating and cooling far more than any other metal. And furthermore, it's a very poor conductor of both heat and electricity for a metal. One of the other, and perhaps most important attributes for this discussion, is that plutonium is highly toxic. By toxic, I'm putting aside the fact that it can be highly radioactive. Just as an element, plutonium is very poisonous, and it's about as toxic as some nerve gases. It can accumulate in a person's bones, and it's something that you really don't want to mess around with. When plutonium was first being produced in quantity during the Manhattan Project, no one really knew anything about it. One researcher, Donald Mastick, accidentally swallowed a small amount of plutonium chloride, and it was detectable in his body for 30 years. From 1945 to 1947, 18 people actually had plutonium injected into their bodies for testing. One man named Albert Stevens, a house painter from Ohio, was injected with 3.5 microcuries of plutonium without his informed consent. Astonishingly, he lived to the age of 79, 20 years after his injection, and died of a heart attack, not cancer. It is believed that he received the highest accumulated dose of radiation of any human in history. On top of being poisonous and radioactive, it can also spontaneously burst into flame at room temperatures if it's left exposed to open air. There have been plutonium fires at factories that create nuclear weapon components. And as if poison, radiation, and flames weren't enough, Pu-239 can reach criticality at about a third of the mass of uranium-235. This can result in what are called criticality accidents, where people handling enough plutonium can have massive amounts of radiation exposure. While this can't result in an explosion, it can provide a lethal dose of radiation, and such criticality accidents have happened almost 60 times. If this stuff is so nasty, and it is, what's the point of it? Why bother making it at all? Well, as I mentioned before, the initial use was for nuclear weapons. Plutonium-239 is the primary isotope used for nuclear weapons, and it's much more fissile than uranium-235. Plutonium-239 is fashioned into what's called a pit, which is basically a small sphere. Neutron-deflecting substances coat the exterior, which lessen the amount of plutonium required. Since the end of the Cold War, demand for plutonium weapons use has decreased substantially. The quality of the plutonium for reactors or weapons is determined by the amount of plutonium-240 which is in it. Weapons-grade plutonium requires less than 7% plutonium-240, and because the isotopes are chemically identical, you have to separate them via enrichment, just like you would enriching uranium, which is really hard to do. Likewise, plutonium can also be used as a fuel for nuclear reactors. While it isn't the primary fuel used in reactors, there are many experimental reactors that could use plutonium and consume it completely. For both weapons and reactor fuel, there are alternatives to plutonium. However, there is one use for which there really is no substitute, and you pretty much have to use plutonium. And that is for deep space probes. As I mentioned before, plutonium-238 is highly radioactive. This isn't the isotope that's used in bombs and reactors, however. Because plutonium-238 has such a short half-life of only 87 years, it generates a lot of heat. Plutonium-238, if just left to itself, will glow red hot, just like an iron poker in a furnace. Hot enough to boil water. Moreover, it will remain that hot with no outside energy added for decades. In theory, a coffee mug made out of plutonium-238 would keep your coffee warm your entire life. Granted, if you're drinking out of a coffee mug made of plutonium, your life might not be very long, but the point remains, it's hot for a really long time. So, what does this have to do with space probes? Solar panels can provide sufficient energy so long as you are sufficiently close to the sun. Even rovers and orbiters sent to Mars can get sufficient power from the sun through solar panels. However, beyond Mars, the light of the sun just isn't strong enough to use solar panels. At Jupiter, for example, the brightness of the sun is only 4% of what it is on Earth. So, how can you power spacecraft that are that far away? The answer is with something called a radioisotope thermoelectric generator, or RTG. What an RTG can do is take advantage of something called the thermoelectric effect, which can convert heat directly to electricity. While there are 22 known isotopes of radioactive elements which could in theory power an RTG, there is only one that can actually practically power it, and that is plutonium-238. The thermoelectric effect isn't that efficient, so it's seldom used on applications on Earth, as it's more efficient to boil water and turn a turbine. One terrestrial use of RTGs was nuclear-powered lighthouses created by the Soviet Union. These lighthouses had no staff and just operated on autopilot. Another use, believe it or not, was plutonium-powered pacemakers. There are probably a few dozen people in the world that still have these pacemakers installed in their body. The RTG was about the size of a watch battery. So long as the plutonium remained fully encased inside the container, the toxicity and radiation really aren't that much of an issue. Plutonium-238 is an alpha emitter, which is a type of radiation that can easily be blocked with as little as a piece of paper. In deep space, there really aren't a lot of options, which is why almost every probe sent past the orbit of Mars and several Martian landers, including the Viking landers and the Curiosity rover, have had plutonium-based RTGs as their power source. There have been some RTGs used in satellites in Earth's orbit, and some were used on the Moon, but it really isn't necessary to use them anymore as solar cell efficiency has become so much better. Also, you don't want to be putting plutonium on something that might re-enter the Earth's atmosphere. A single kilogram of plutonium-238 is about the size of 2 marshmallows, or a bit bigger than a golf ball, and can give off 500 watts of heat continuously. RTG fuel is usually in the form of pellets of plutonium dioxide, and the amount can range from a few kilograms to as much as 35 kilograms. One problem NASA had recently was a shortage of plutonium. The United States stopped making plutonium-238 in 1988. NASA started buying it from Russia in 1993, a whopping 16.5 kilograms of it, but they also stopped producing it as well. The U.S. government actually started to make plutonium-238 for NASA in 2015 for the first time in decades, albeit the amount produced each year is still quite small. It takes about 2 to 3 years of exposure to a nuclear reactor to make a batch of plutonium-238. Current production is only about 400 grams a year, but they hope to triple that by the year 2025. The extreme cost and difficulty in the production of plutonium-238 makes it one of the most valuable substances on Earth. Plutonium is serious stuff. It's extremely toxic and radioactive, but thankfully most of us will never encounter it in our lives. Nonetheless, certain isotopes of plutonium have properties that no other isotopes of any other elements have. And if it wasn't for plutonium, we simply wouldn't be able to explore the outer solar system. The associate producers of Everything Everywhere Daily are Peter Bennett and Thor Thomsen. If you'd like to support the show, please join the list of patrons over at patreon.com. And also remember, if you leave a review or send me a question, you too can have it read on the show.